So now we're moving on to another kind of function. So just in case, or maybe to give you sort of a little bit of a big picture, just sort of summarizing the portion of the class that we're in right now, we're in the part of the class where we just really focus on different kinds of functions and how they act and the sort of things that we can do with them and the kinds of behavior that they demonstrate. So earlier in our class, we talked about linear functions. We just finished talking about quadratic functions. And now we're going to move on to polynomial functions, which is kind of like the next step up, okay? We've studied polynomial expressions already in our class, so I think you should find between the discussions that we've already had on functions and the discussions we had way back when on polynomial expressions, I hope that you will find that this discussion that we're going to have on polynomial functions is really combining lots of ideas that we've already talked about. And hopefully you'll find that there are large portions of this section that feel like review to you, or at least should seem somewhat familiar. And that's kind of where we are in our class, that we're going to keep cycling back to old ideas and incorporating incorporating those old ideas in new ways. Okay, so with that said, let's take a look at the learning objectives and talk a little bit about what we're going to be doing with polynomials. The learning objectives here actually are quite a lot. So there's only 3 learning objectives written on this paper, but by the time we finish our section on polynomials, you're going to see that those 3 learning objectives, they represent kind of a lot of information. So the first one is finding x-intercepts. And notice that I've even outlined the way that we're going to do that when we study polynomials is we're going to substitute 0 in for y, and then we're going to factor. Okay, now realize that's exactly one of the methods that we learned with quadratics. Plug in 0 for y, well, that for sure is exactly the same. And then we talked about with quadratics that you could either factor or you could use the quadratic formula. Well, unfortunately, for polynomials in general, there's not a formula. There is one specifically for quadratics, but as you get into larger degree polynomials, there isn't a formula. And so we're going to rely heavily on factoring. In fact, I'm going to jump down to number 3 here. Use factoring techniques, common factoring techniques, to do a complete factorization. You'll find that this is where we're going to spend most of our time, is reminding ourselves of old factoring techniques and possibly learning 1 or 2 new ones so that we can do a factorization. Because with polynomials in general, as I've said, there's not a formula to use. So we just simply will need to be able to factor. Okay, then this middle objective is really just a vocabulary thing. We need to recognize that x-intercepts, for the purposes of our class anyway, are basically the exact same thing as finding zeros, finding solutions, and finding roots. Okay, so we're going to talk a little bit about that. This really becomes more important when we start getting into the applications of polynomials, because it's clear when we're making a graph that we're looking for x-intercepts, but the fact that those are solutions maybe is less clear. And so as we start getting into this, this really just simply becomes a matter of semantics. I suppose maybe in the interest of full disclosure, if we were to split hairs a little bit, at a more advanced level of math, I'm sure there are mathematicians that would tell us that there is a slight difference between an x-intercept and a solution, or an x-intercept and a root. That there are subtle differences between these things. But for the purposes of our class, we're going to do a high enough overview of this material that these things are exactly the same. Okay, we're not going to consider them any different. But there we go. So with all of that said, why don't we go ahead and get started by just sort of talking a little bit about the broad notion here. Okay, so if I look at a polynomial graph, I've got a couple polynomial graphs here. These are the sorts of things that we're going to study. So you'll see these are just 2 examples of polynomial graphs, but you'll see they have a couple things in common. First of all, they've got a series of hills and valleys. I suppose some people would say, hey, look, if you just took one of these, either valleys or hills, whichever, isn't that sort of kind of like a parabola? And the answer is that it is sort of kind of like a parabola. And so technically a quadratic function is just a specific kind of polynomial, but there are larger polynomials. And what happens, we'll see, is as you look at polynomials, I'm just making one up here, so this doesn't come from any place in particular. But as you look at polynomials, in general, the larger the exponent becomes, the larger the degree. That was the vocabulary word for the largest exponent. The largest exponent was called the degree. The larger the degree becomes, the more hills and valleys, generally speaking, our polynomial is going to have. So with a quadratic, it just had one little either hill or valley. This was an example of a cubic. It has two little hills and valleys. This would be something that's raised to the fourth degree. So there's three little hills and valleys. And so you can see there's a definite connection between what the degree of the polynomial is and how many hills and valleys there are. There's also a definite connection between the degree and how many times it could potentially cross the x-axis. So with our quadratic in our last chapter, we talked about the most it could ever cross is 2. There are times where it crosses only once or even 0 times, but the most it could cross is 2. That was a quadratic. But with something like a cubic, something the third degree, the most that could happen is 3 times, okay? This is an example of a fourth degree. Now, this particular one crosses only twice, but you can imagine if my graph was just a little bit lower so that the x-axis was like crossing up here, I could potentially have 4 intercepts going across, right? So the number of times it crosses the x-axis is also going to be related to that number. All right, so this is just some general overview of what we're going to be talking about. As I said, the way that we're going to find these x-intercepts or solutions or zeros or whatever you want to call them, the way that we're going to find those things is through a general process of plugging in 0 and then factoring. All right, now let's talk about that for just a second because the concept behind this is important. And it's a concept that we've discussed off and on in our class. So hopefully we're pretty good with this. First of all, why do we plug in 0? And second of all, what do we plug 0 in for? Okay, so this is something that we've talked about recently, just as we've studied quadratics. If I want to find the spot where I'm crossing the x-axis, I need to realize in the case of this particular example, 1, 2, 3, 4, 5, that every single point on the x-axis, 1, 2, 3, 4, 5, 6, 7, 8, 9, every single point on the x-axis has this feature where the y-coordinate is equal to 0. And it doesn't matter which point I pick, the y-coordinate is always equal to 0. And that should make sense to us because the y-coordinate describes how far up or down I've gone from the origin. And if I am on the x-axis, then I have not moved up or down at all. And that's true no matter what kind of graph we're talking about. It's true for something with a big exponent. It's true for something with a smaller exponent. It's true even if we're just talking about lines, right? If I just take a line, that x-intercept is still a place where y is equal to 0. So it doesn't matter what kind of function we're talking about. Anytime I'm on the x-axis, at that place, the y value is going to equal 0. Okay, so this is a general rule, not just for lines, not just for quadratics, but for all functions, for everything in mathematics. It's always the case that all points on the x-axis have 0 for their y value, or y coordinate, you might say. Okay, all points on the x-axis have 0 for their y coordinate, for their y value. And so what we do is we leverage that when we're trying to find points on the axis. Okay, so this really becomes the first learning objective that we talked about. The way that we find y-intercepts is by plugging in 0. I'm sorry, the way we find x-intercepts is by plugging in 0 for y. And so this, I'm just going to say recall because we have talked about this before. So to find x-intercepts, substitute 0 for y. Okay, so we're just leveraging the fact that every single point on the x-axis always has this feature that the y value equals 0. And since we know that's always true, then one of the ways that we can find x-intercepts is to plug in 0 for y. This is one of the reasons why they call them zeros, okay? Because we're just plugging in 0. That's what we're doing. We're plugging in 0, okay? So that is a general rule that's true for all functions, not just polynomials or quadratics, but that's true for all functions, always. Okay, so now what about this next piece of factoring? This is also something that we have talked very briefly about, although it's been quite a while since we've talked about this. Remember, a general idea in math is that if you have two numbers, as I write these down, just think about what I'm doing here. I've got two numbers being multiplied. So when we multiply two numbers, okay, one of the things that we know, in fact, it's so basic that we usually don't even talk about it. And so some people, even though they know it, they're not, aware of it, right? Sometimes there's a difference between knowing things and being aware of things. That when I multiply two numbers together, there's a particular answer that I'm going to get. And the product of those two numbers is always equal to that answer. It doesn't ever change, right? 2 times 3 is always equal to 6. There has never, ever, ever been a time in math where somebody has done their math correctly and after multiplying 2 and 3 ended up with some other number. That doesn't happen, okay? And similarly, I can take, 3 and multiply it by 0, and I know that I'm going to end up with 0. It's always the case when I multiply 3 times 0, I always get 0, okay? But it turns out that there are other rules that we can build off of this, okay? Like, for example, multiplying 3 times 2, we can say anytime you multiply a number by 2, the answer is even. Okay, anytime you multiply a number by 2, the answer is even, right? 6 is an even number, right? 2, 4, 6, 8, 10, these are even numbers. Anytime you multiply a number by 2, the answer is even. This is a general rule that we can make. Okay, now, how useful is that rule? I'm not sure. I believe there are times when it's useful, but is it generally speaking useful? I don't know. But this is a true rule. And maybe a more useful rule that we have talked about in our class is if you multiply a positive number times a positive number, your answer will be positive. But if you multiply a positive number times a negative number, if I were to insert a negative right here, a positive times a negative will be negative, right? And so these are all general rules that we have learned in math, and they're so basic and fundamental that we don't really talk about them very often, but those are true. There is a general rule that goes with this little product that I have here as well. Anytime you multiply something by 0, it doesn't matter what the something is. Anything times 0 just happens to equal 0. Anything times 0 is always equal to 0, and that's something that we know. Again, we don't always talk about it, but we know it. In fact, this goes one step further. If we want to think about the formal logic that you studied in geometry class, this is what we would call a biconditional statement, because it's true that anything times 0 equals 0, but it's also true that if 0 was the answer, then you must have been multiplying by 0. In other words, there's no other number that I can multiply by to get 0 as the answer, right? I could sit here and multiply 3 by numbers all day long, The only time I'm going to get 0 as the answer is if I'm multiplying 3 times 0. That's it. That's the only time. There are no other numbers when I multiply them by 3 that I get 0. And that's true for anything. There's nothing I can multiply 2 by to get 0 as the answer except for 0. So this is a very strong statement. And then what it does is it lets us recognize things like this. If I have two numbers and I don't know what those two numbers are, okay, so we're playing, guess my numbers here for a second. I don't know what these numbers are. These are just two random numbers. These are two unknown numbers, okay? But if I told you that when I multiplied them together and the answer was positive, you would be able to tell me something about these numbers. You would know that they both have the same sign. Either it's a positive times a positive, or it's a negative times a negative. But it couldn't be anything else. If I told you that when I multiply them together, the answer is negative, you would know something about them. You would know that one of them has to be positive and one of them has to be negative. Now, which one's which? Don't know, okay? But so I can give you clues and hints about my two numbers, and you would be able to tell me something about them. In this particular chapter, the clue and hint that we will use the most is if we multiply them to get 0. Anytime we do that, we know, whenever that happens, we know, it's guaranteed, there's never an exception, that one of the secret numbers must be a 0, because there's nothing else that you can multiply to get 0 as the answer. So for example, it might be the case that the first number was 3 and the second number was 0, like I had before. Now, I don't know for sure if that's the case, but it might be the case. It might be the case that the first number was 0 and the second number was 3. Maybe. Don't know for sure, but it might be. But the bottom line is I do know that one of them is 0. This right here is the part that I know for sure, that one of them is 0. And so that's how we leverage finding zeros or finding x-intercepts or whatever we want to call them with polynomials. We factor them. In other words, we get them to a place where I have two things multiplied together. We set them equal to 0 because I know that every point on the x-axis has a y value of 0. And then that lets me figure out, well, either it's got to be this one or it's got to be this one. And then I can find the answer from there. So with all of that as a background, let's take a look at the first type of problem that we need to be able to solve. If I know that x plus 2 times x minus 3 times x plus 5 times x minus 4 is equal to 0. What are the possible values of x? Okay, what are the possible values of x? Now, this is finding a solution, right? We've got an equation and we're going to solve it. We're going to find the possible values of x. We're finding a solution. But it's a solution specifically when y is equal to 0. So that's one of the reasons why we said x-intercepts are actually the same thing as solutions. I know the y value has to equal 0. I plug in 0. Now I solve for x. It becomes a solution. So this is the general idea of what we're talking about. So what I have is I have a total of 4 things being multiplied together. 1, 2, 3, 4. And when I multiply them, their answer is 0. So this goes back to this exact notion. That means one of them has to be a 0. So the way that we solve this is we simply set each one equal to 0. Now, there is a certain sense in which I don't know which one actually equals 0. I mean, it could be that they all equal 0 because 0 times 0 times 0 times 0, that does equal 0. But what we'll see is if they all equaled 0, then x would have to simultaneously be different numbers. And that sort of breaks our rules for math. So that's probably not the case. However, I know that there's no other options. It's got to be the case that at least one of these is 0. And so if I go through and I solve this, x subtract 2 from both sides, x is -2. Add 3 to both sides, x is +3. Subtract 5 from both sides, x is -5. Add 4 to both sides, x is 4. Okay, so I end up with 4 possible options of what x could be. Now, again, possible. I don't know for sure which one x currently is, but there's no other things that it could be. Because there's no other number I can multiply to get 0 except for 0. So there's either this thing equals 0, in which case x has to be -2, or this thing equals 0, in which case x has to be 3, et cetera, et cetera. It's got to be one of those cases. There's no other options. And so these are the only possible values for x. And so this is the general idea of what we're doing. Now, of course, the challenge becomes getting your polynomial to look like this. That becomes the challenge. And so really from this point forward, what we're going to be doing with our little unit here on polynomials is reviewing the different factoring methods to get to this point. All right, but this is the main idea. If you have it equal to 0, and if you can get it factored, then by setting each factor equal to 0, that lets me determine the possible values of x. Now, there is one last comment that I think is probably worth mentioning. Notice that there's a definite connection between the way the factor looks and what the actual answer is, right? It's really just this number with the sign changed. So there is a certain amount of shortcut that you can take as long as you're careful. Now, here's what I mean with as long as you're careful. Just suppose, for the sake of argument, that this wasn't an x plus 2, that this was a 3x plus 2. If that's what we had, was a 3x plus 2, then when I set it equal to 0 and I solve, I don't get x equals -2 anymore. Now I get x equals -2/3. Okay, so there is definitely a connection between the actual solution, the actual x-intercept, the actual factor, or I'm sorry, root, whatever you want to call this number, and the factor. There's definitely a connection between those things. And when the factor does not have a coefficient in front of, or when the coefficient is 1, maybe is the better way to say it, then that connection is very easy to see. And it is perfectly acceptable for you to use that connection to find the answer and not necessarily have to show these steps every time. Okay, so here's where we are right now. We know, we have reviewed in this video why it is the case that plugging in 0 for y helps me to find x-intercepts. We've also reviewed in this video why factoring helps me to find solutions to these equations. We've talked about in the video that these things are basically the same word for us, okay? In our class, that x-intercept, 0, solutions, and roots, those are 4 words that all mean the same thing. And we've talked about that there's going to be a need to factor. If factoring is the method, there's going to be a need to factor. For this video, part 1, this is where we're going to stop with this overview of why these things work. And then I'm going to make some more videos where we go back and we review the factoring techniques that we've learned previously in our class and get to the point where we're comfortable with the idea of a complete factorization and what exactly that is. All right, but that's it for this video. Thanks for watching.